HLAA, vectors, day number 1. Today we're going to talk specifically about vocabulary and some properties of vectors. So let's get right into it. Okay, some basic vector terminology, the first of which is the line segment. You can see the notation used here with the square brackets. That represents part of a straight line bounded by 2 points and denoted, of course, bracket AB. So that just represents some line segment, no particular direction involved, but just the physical element of a line segment. The second term is called a directed line segment, also known as a vector. This is a line segment that has direction, i.e. there is a start and an end point. We call this segment vector AB, denoted mathematically by the notation AB with an arrow over it, where A is the starting point and B is the ending point. Okay, so you'll have a point A, you'll have a point B, and you have this direction, right, with a start and an end. Equivalent line segments, next term here, are two directed line segments, AB and CD, are considered equivalent. Notation for that is this congruence symbol that we normally see in geometry, if and only if the line segments AD and BC have a common midpoint. So let's go ahead and sketch this out. Here is the directed line segment or vector AB. Right, and typically you won't see the arrow necessarily on the diagram. So you'll just see two endpoints, A and B. You're just implied that the direction is from A to B. And another directed line segment, C to D. Okay, these two are equivalent, meaning they have the same direction and the same, what we'll call magnitude in a minute here. If AD and BC have a common midpoint, meaning that they bisect each other. Okay, we can see that both have a midpoint at that point of intersection. I could call it M. Therefore, those two directed line segments, AB and CD, would be equivalent. All right, example 1. This typically is a really good way to look at this, but if I were to enclose these two vectors, AB and CD, but I'm going to call them P and Q and R and S. Not my best sketch, but it'll do. Okay, if I have a parallelogram, PQRS, okay, meaning opposite sides are parallel, that tells me that the opposite sides are headed in the same direction. So QS would be headed in the same direction as PR, and PQ in the same direction as RS. Given the parallelogram PQRS, find all possible pair of equivalent directed line segments. Okay, so one of the properties of a parallelogram is that opposite sides are parallel and opposite sides are congruent. That tells us that both the direction and the magnitude of the opposite sides are the same. So I can see clearly in a parallelogram that pairs of equivalent directed line segments would be PQ is equivalent to RS. And this is not all that interesting because we know, right, clearly PR equivalent to QS, right? This is pretty basic stuff. But what you couldn't say is you couldn't say that PQ is equivalent to SR, right? You can't say that because they don't have the same direction. They might have the same length, which we call the magnitude, but they don't have the same direction. Okay, so I would have 4 pairings. Here's pairing 1, here's pairing 2, and then I could take each of those and reciprocate them. So reciprocate was the wrong word, but I could say that, I guess invert them. QP is equivalent to SR, and of course our fourth would be RP equivalent to SQ. So when talking equivalence, two things have to be kind of checked off the list. Direction is the same, and magnitude. We're going to talk about that on the next slide, I believe. And kind of a part C to that, the diagonals of the enclosed quadrilateral bisect each other. That's a special way for saying bisect each other, that they share a common midpoint. All right, let's continue on the next slide. Okay, some more basic terminology. Collinear points are two or more points on the same line. Okay, so here let's have a directed line segment from A to C through B. Okay, clearly A, B, and C are collinear, and I've got point D hanging out over here. D is not collinear with the others. Coplanar, lines and points can be coplanar if they lie in the same plane. So a plane, not as easy to visualize, but let's say I've got this, and I've got point A, and I've got line segment BC. I could say that A and B and C are coplanar. Okay, a vector. A vector is a collection of all possible equivalent directed line segments. Vectors are defined by their direction and their magnitude, which we call length. So I could draw an infinite number of vectors, right, of, let's say, length 3 on, that wasn't the same length, but whatever, on this digital page here. These are all equivalent vectors, provided they head in the exact same direction and they have the same magnitude. A displacement vector is typically represented, how we've seen on the previous page, in this notation, one of these two. So AB or AB with the arrow over the top of it, where A is the initial or starting point and B is called the terminal or ending point. Now, opposite vectors are interesting and actually come up quite a bit. AB and BA are opposite vectors as they have the same magnitude but opposite directions. Thus, we can say that AB is the opposite of BA. All right? And when it comes to opposite, this represents direction, right? So this multiplier, right, which we have a -1. Okay, so the magnitude of a vector is the length or the displacement vector, and it's denoted using this notation here. So for example, let's say I have a vector that heads from the point 0, 0 to the point, I don't know, let's call that 3, 4. Well, how could I find the magnitude of that vector? Let's call this vector, I don't know, CD. Okay, so there's CD. The magnitude of that vector I could actually utilize, and we're going to look at this in a future lesson, but I could utilize Pythagorean theorem. So I'd use a 3 and a 4, which clearly would give me the magnitude, which would be a 5. So Pythagorean theorem is interesting, as well as the angle at which a vector travels. So we're going to talk about those in future lessons. Let's continue to the next slide. Okay, addition of vectors. There's two rules that we typically use. One's the parallelogram rule of vector addition. The other is the triangle law or rule of vector addition. Both are very similar. Let's say I have a parallelogram A, B, C, D. Okay, so here's A and B and C and D. It's traditional methods to kind of travel around the object, not bounce around it, right? So meaning I wouldn't put D here and C here because we want to keep them in order. Okay, so the parallelogram law of addition says that A to B, right, this vector here, plus B to C, oops, I'm sorry, A to B plus, this should actually be, oh, okay, let me write it out this way. I don't like the way my notes are written out here, but A to B plus B to C should equal this resultant vector, A to C. Now, you can see that I've got noted A to D here. Okay, so A to D is actually an equivalent, because this is a parallelogram, is equivalent to B to C. All right, this vector BC. Okay, so essentially what I'm doing is I'm just taking this vector AD, shifting it up, and it becomes BC. But that is the parallelogram law of vector addition, right? So I can say, provided I end up where I want to finish, I could get to, C however I want to. So I could technically say that AD plus DC actually gets me the same vector AC. Okay, the triangle law, very similar. Say I have a triangle. This is a little bit more basic, but let's say I have a triangle ABC. I can get to C a couple different ways. Well, only one, well, I guess two ways, but if I want to write the vector AC, I could write it as AB plus BC, right? Clearly, A to B plus B to C gives me kind of a roundabout way to go from A to C. Now you'll notice that as you look at vector addition specifically, you're kind of jumping letter to letter. So A goes to B, B goes to C, therefore A goes to C. It's kind of like the transitive property of addition. Okay. Given the diagram below, draw AB plus CD plus EF. So what I'm going to do is really what I want to draw is A to F. Now these are all these vectors are located in different locations here, and they don't like end up tip to tail. So what I'm going to do is just translate them. So I'm going to take AB, which is this vector here. Looks like it's got a magnitude of 4. I'm going to translate C to D to where the tail of CD ends up at the tip of B. So it looks like CD goes right 1 and up 3. So I'm going to go right 1 and up 3 from B to the translated location of D. And then I'm going to take the vector EF, and it looks like left 2 and up 2. And therefore, this vector right here, let's put it in blue. That blue vector right there would be AB plus CD plus EF, which we could call AF. Okay, let's look at kind of an interesting idea of showing that a property is true. So think of this as, we're traveling a total of 0 units, right? So clearly in a triangle, if I went from A to B and B to C and C to A, right, in this order, right, so here's my vector addition properties showing up, that I should end up exactly where I started and hence have traveled 0 units. Even though I've not traveled 0 units, I've ended up 0 units from where I started. So it's kind of like displacement in essence. Okay, so let's use a definition. Okay, so I know that AB plus BC is equal to AC, right? So what I'm going to do is I'm going to replace the first 2 displacement vectors with AC. And I'm going to add AC to CA. Now, recall back to opposite vectors. These two are opposite vectors. Therefore, C to A is equal to the opposite of A to C. And you can kind of see how this is going to negate and reduce to 0. Therefore, by definition, a to b plus b to c plus c to a is equal to 0. Okay, let's continue. All right, scalar multiplication, multiplying a vector a by a non-zero scalar k results in a new vector. So look at this. This vector a, when multiplied by a scalar, becomes a new vector b, such that b has the same direction as a when k is greater than 0, and opposite direction when k is less than 0. So let's take, vector a. And I don't have endpoints for this, but here's vector a. Okay, if I take and multiply a times k, and let's say k is greater than 1, okay, ka ends up being, let's say k equals 2. Well, that would look like this. Same direction, different magnitude, right? The magnitude would be k times the magnitude of a. So the magnitude of ka is going to equal the absolute value of k times the magnitude of a. Right? Because technically speaking, let's say k equals -2. There's absolutely no difference in the magnitude of those two vectors, just the direction. That's why we take the absolute value of k times the magnitude of a. All right. Let's look at the rest of the properties here. The magnitude of b is the product of the absolute value of k and the magnitude of the vector a. Therefore, the magnitude of b is equal to, like we said, absolute value of k times the magnitude of a. All right, a vector and the vector obtained by multiplying the original by a scalar have the same or opposite directions depending on the sign of k. We talked about that, and are said to be collinear or parallel. Okay, so if k is less than 0, it just changes the direction. If k is greater than 0, the direction is the same as the original vector. Let's talk about linear combinations. Given two non-collinear vectors, a and b, we say that a linear, not the vector a, but a linear combination of those two vectors is a new vector. So let's say I take a and multiply it by some value, and b and multiply it by some value. So I'm doing a scalar product, right, of both a and b. So here I've got vector a in this diagram and vector b. We could draw the following linear combinations. Now, if I took 3 times a plus 2 times b, I would get some new vector c. Let's put c in yellow. Okay, it's going to be hard to draw this, but 3a, there's 1a, 2a, 3a. This is an attempt. Okay, so this new vector, let's call this 3a. Okay, and then it looks like 2b. So here's 1b, 2b. Of course, tip to tail. You can imagine that that's a 2b. So this new vector c would look kind of like this. So c, which equals 3a plus 2b, would look like that. Okay, I'll leave the second example for you. Of course, you'll do half a minus 2/3 b. Actually, you know what? Never mind. I'm going to do that one because there's some subtraction going on, and I'd like to see that happen. Okay, so here's the original a. So I'm going to take half a, and I'm going to kind of translate it to a new spot. Here's half a minus 2/3 b. Okay, so here's b. Here's b tagged onto that. So if this were, let's say this were our new vector, right? This would be the vector half a plus b. But I want minus 2/3 b. That means I'm going to send this vector b in the opposite direction, 2/3 of the length of what it was before. This would be our resultant vector. This would be half a minus 2/3 b. Very cool. All right. Now, it doesn't really matter where I sketch this as long as I go tip to tail with the two resultant vectors. All right, let's continue. Okay, so here's where things get a little bit abstract and, well, uncomfortable, to be honest, at least at first. So in a triangle ABC, M and N are midpoints of the sides AC and BC respectively. So let me label that just so we can see that M is the midpoint here, and N is the midpoint here. Show that MN is parallel to AB, so I want to show that this is true, and that MN, that length, is half of AB. Okay, so first we need to kind of establish an idea. If MN is parallel to AB, then the vector MN is equal to lambda, some real number, scalar product, times AB. Okay, so let's work with what we know. Let's use the triangle law to set a couple of things up. So I know that AB is the sum of AC plus CB. This is by the triangle law. I also know that MN is equal to MC plus CN, triangle law yet again. All right, so since M, and all this is necessary, guys, you got to lay this out, is the midpoint of AC, right, that's segment AC, and N is the midpoint of CB, then what I know is that MC is equal to half of AC and CN is half of CB. Okay, we've established a few items here. Okay, so what I'm going to do is I'm going to take and write the sum of MC and CN, which I already know in the back of my mind is MN, but I'm going to write it as 1/2 AC plus CB. You see what I did there? I took half AC plus half CB and wrote it as half AC plus CB. Now, by definition, this is MN, and this right here is AB. Okay, thus, MN is parallel to AB. Right, it proved what I started with. Right, I wanted to show this. So my if then was really a what I want to show, and then I got into the meat and potatoes there. Okay, and if MN is equal to half of AB, then the magnitude of MN, of MN is equal to half the magnitude of AB. Therefore, MN, which is a different way to note the magnitude, just means the length of MN. It doesn't really consider direction, but it doesn't matter, is equal to half AB. I would say that this isn't necessarily necessary there. I think you could finish, I would say you could finish right here and feel comfortable with that result. Okay, we got one more abstract example here on the next page, and then we'll be done for lesson number 1. Okay, here we go. Example 6, last one for this video. Given a regular hexagon A, B, C, D, E, F, and midpoints M and N of sides EF and CD respectively, use vectors to show that the lines MN and AB are parallel and that MN is equal to 3/2 AB. Okay, so I'm going to note here that, first of all, this is a regular hexagon, so all outer sides are congruent. Therefore, these two segments are actually equivalent to these two segments. And it doesn't really help us, but it's nice to note and might be helpful later on. Okay, so if this is what I want to show, MN is parallel to AB, same letters actually of the previous example, then MN is equal to, I'm going to use a different variable, mu times AB. Okay, so let's find mu in this case. Okay, and clearly mu is going to equal 3/2. That's where we're headed with this. Okay, so by definition, AB is equal to AO using the triangle law plus OB. And MN is equal to, this is where it gets a little messy, ME plus EO plus OD plus DN. Okay, by the definition of a regular hexagon, okay, so because I know that I have a regular hexagon, I know the following is true. I know that EO is equivalent to OB, same direction, same magnitude, and OD is equivalent to AO. Okay, we're going to see a little bit more with that in a minute here. Okay, thus, MN is equal to ME. All right, now I'm going to sub out here. EO plus OD. Well, EO plus OD is equivalent to OB plus AO. So AO plus OB is actually equal to AB. Okay, you can see what I did there. I'm doing a substitution of equivalent vectors. Okay, now, and then of course I got to tag on a DN. All right, so here we go from here. Since M is the midpoint of FE, and FE, by the triangle law, is equivalent to AO, as well as N is the midpoint of DC, and DC is equivalent to, oops, I forgot my little squiggle there, is equivalent to OB then ME is equal to 1/2 FE, which is equal to 1/2 AO. Okay, I could see that kind of tied together in this statement here. And DN is equal to 1/2 DC, which is equal to 1/2 OB. Okay, so why did I do that? Let me go back to where I wanted to kind of get that, the intent of that. I want to replace ME with 1/2 AO and DN, let's do this, let's go blue, and DN with 1/2 OB. Why did I want to do that? Because now, therefore, MN is going to be equal to 1/2 AO plus AB plus 1/2 OB, which if I combine the green and the blue, I end up getting 1/2 AB plus AB. So MN is equal to 3 halves AB. All right, hence MN is parallel to AB. Right, I found mu is equal to 3 halves. So they head in the same direction. And MN is 3 halves the length of AB, thus, as well as MN is equal to 3 halves AB. All right, guys, that's it for lesson number 1 for vectors. We'll see you in the next video.